let's look at projectile motion. It is one of the more advanced things we do in kinematics, but I'm sure you'll find it rewarding and a bit of a challenge, but it really boils down to bookkeeping and good decision making. Here is the list of things that you need to be able to do to be prepared for grade 12 physics. The first thing we want to look at is the idea of independent axes. You can go onto Wikipedia, look up projectile motion, and you will find this animation. It would have been a lovely lab to do in school. You will find when you drop an object and you see the trace of its points in time on the left that say this was a 10-second fall. If at the same time you shot another object off with horizontal speed, it would still take 10 seconds to fall. In other words, jumping off a cliff and running off the end of the cliff, you will hit the ground at the same time. The vertical fall is unaffected by the horizontal movement, regardless of what you've seen on the Dukes of Hazzard. The biggest change to study projectile motion is that we are plotting distance on both the vertical and horizontal axis. So this is the actual path through two-dimensional space and not a distance time graph. It is really important that you understand the difference. We are breaking the motion into vertical and horizontal components using trigonometry. The side axis is distance. Pilots say never let the plane take you somewhere where your brain hasn't been 5 minutes before. Don't let your eyeballs and the graph take your brain someplace where your math isn't ready. If you haven't taken a moment to read what the graph is about, you will make mistakes. Now we're going to see there's a difference between teaching vectors and breaking them down in trigonometry. Writing the speed on the x and y axis here where there's an imaginary particle that we can't see makes sense, but it doesn't help us do trig. We have to rearrange the vectors into a triangular form. So to graphically add them, this looks nice when you're picturing that this object has a horizontal speed and a vertical speed that combine to the trajectory in space, but you can't do math on them that way. You have to rearrange them like this, but sometimes your brain will go, hey, what do you mean? This velocity vector is not even affecting that particle over here. It is. We've just moved it over so we can do basic trig with it. So let's try a simple example using this. We're going to fire a projectile at 100 meters a second, 45 degrees up. You are used to computing the slope of the line, but that is on a distance time graph. These are velocity vectors on a distance graph. The slope of a DD graph has no physical meaning and has nothing to do with the velocity vectors displayed. Don't misunderstand these graphs. You use them to break down the velocity vector into a horizontal vector called Vx and a vertical velocity vector called Vy. We can do this by placing a labeled triangle next to it if you need. You see Vx is the adjacent side, Vy is the opposite, and the bright blue velocity primary vector is the hypotenuse. And with these ratios, we can break down the velocity in blue into its separate x and y components that make it up. First example, we label our triangle. We know the hypotenuse is 100 meters a second long. We know the angle is 45. So adjacent over hypotenuse is the cosine of the angle. Here is our first example. We have an adjacent and a hypotenuse side. The adjacent side is the equivalent to the Vx. So to get the Vx side, we need to link the adjacent to the hypotenuse. That's the cosine function. So we write it out. Adjacent over hypotenuse is cosine of theta. Now we're going to replace with the general mathematical term adjacent with our specific term in physics, Vx. And the hypotenuse we are calling velocity. We swap it out like that. This gives us this formula. Vx is v times cos theta. That's the first component in the horizontal. Let's do the vertical now. The vertical needs to connect the opposite side to the hypotenuse. The opposite side is Vy. The hypotenuse is the full velocity. There's the trig symbol. Opposite over hypotenuse is sine of theta. We replace opposite with what it is in physics, Vy. We replace the hypotenuse with V, and we rearrange and we get this formula. This is bread and butter rearrangements you will need for eternity if you keep taking physics. They will be used constantly. Not in every unit, but they are going to be the backbone of all motion physics going forward. So you really want to get them while school is free. So I'm going to put them both on the same screen. We have our ratios at the top. We've already done them. We now have an X component and a Y component. So you break your page into two sides, a vertical and a horizontal side, and keep them separate from each other. So in the X direction, if we carry out the math on the left, you can see that 100 meters a second times cos of 45 is 71 meters a second. And I put X in brackets. I just like to be redundant that way, just to make darn certain I don't swap my X and Y values. On the right side, using sine theta, we also get 71 meters a second in the vertical. Holy moly, they're the same. Of course they are. A 45-degree triangle is half of a square. The two sides are identical in length. That's exactly what we should have got. You try Pythagoras, square them and add them, you'll get your original number back. So I chose 45 because it's one of the simplest ones to do. So confirm it. If you're at all paranoid, double check. We now treat the problem as two separate problems, one in the vertical, one in the horizontal. Typically, the vertical component is the most important one because it will determine the time of flight, and the time is everything in these problems. So we're now looking at a one-dimensional problem. How long does a projectile fly when launched at 71 meters a second vertically? Doesn't matter that it's traveling sideways as it goes. Every time in your life you've jumped vertically, the Earth is roaring its butt off to the east. It has no ability to affect things that way. When you're at the equator, you're ripping along at more than 1,000 kilometers an hour to the east. It has no bearing on you falling to death. It's a completely different direction. Given these four variables right there, we already have enough to solve for time. But the time we get is to the peak of the flight, not up and down. It's only one way. To find the time was easy, and the distance is just as easy. We can use this formula. VF disappears because it's 0. We rearrange to have divide by 2a on the far right. You could write 2g to make it clear to yourself you know it's gravity. Plug in our numbers and we get 252 meters upwards. Now this is a symmetrical problem. If it took you 7.1 seconds to go up, it's going to take you 7.1 to come down. The only change would be you're now starting with a VI of 0 and a VF of 71 downwards and a distance which is downwards. So you can usually claim symmetry, but if a teacher requires proof, you just recalculate and just relabel and change the signs on your distance and your speed. We'll switch to the horizontal. This now is controlled strictly by two variables, the time of flight and the speed in the x-axis. There is no acceleration there. So you can write VF and VI as the same number or just write V. It doesn't hurt to put in an acceleration of 0 to remind you not to insert an acceleration if there isn't one in that direction. And we're going to compute D. The time we have to double though, because the time of flight was only 7.1 seconds up. We double it for the way down, and it's a very rudimentary problem that gives us 1,008 meters horizontally. So that's a simple example of breaking a problem down into two directions. The vertical flight determines the time, and the time tells you how long the projectile has to move sideways before it runs out of time. We set up our formulas and our trig, and we can start the computations. The horizontal and the vertical have nothing to do with each other. We run the trig calculation, we get 188 meters per second in the vertical, 68 meters per second in the horizontal. This makes logical sense because a 70-degree launch angle would indicate we're shooting up more than sideways. Now we set up our two sets of variables. These are two independent problems now that have nothing to do with each other. I put in A is equal to 0 or don't even include it at all on the left-hand side. And there's a constant speed, so we really don't have a final speed. We apply our two values we've calculated above, and we start looking now for this distance on the vertical axis. Without time, this is our best bet to solve for distance. And we get 1,767 meters in the vertical. So we've solved that, we can pop it in there. Now, in order to solve for time, we could use two other calculations for it. This one, A equals delta V over T, uses the least number of calculated variables. We do that, we get approximately 20 seconds. Now, the 20 seconds has to turn to 40 when it moves over to the horizontal, because 20 seconds is only till the speed in the vertical fell to 0. In other words, the peak altitude. 20 seconds up, 20 seconds down. And we have a very simple calculation at the end, and we've got it. The shell has had 40 seconds to move horizontally while it was busy flying up to the sky and coming back down. Now, I don't like teaching, here are 10 basic kinds of problem. I prefer to have you develop strategies to solve your problems, but that doesn't mean it's not worth looking at a set of sort of predictable problems, like what are the possible variations I could give you. So let's take a look at a few of them. This is a very common one. Something is in the way. You're shooting a projectile and there's an object in the way, and that prevents you from getting all the way to a 0 altitude again, and you're now hitting the tree or the object at some height above the ground. So the unimpeded range, the full range, has been reduced to some shorter range. So I'm going to invent two numbers, 20 meters a second at 50 degrees up, and the tree is at a distance of 30 meters. We're going to call that dx. The vertical time of flight that we've used up to now means maximum height occurs halfway through the flight. That symmetry has been broken because the tree is preventing this trajectory from being perfect. This causes a change in what we're doing. The time of flight is no longer the dominant situation. The tree is. It's this 30 meters that's ending the problem. So the time now is not the time of flight, it's the time to hit the tree that's driving the problem. So we have to set it up in three ways. We have to break our speed down into X and Y like before, then figure out the time to reach the tree and go backwards to the height. Nothing has changed. It's identifying that key difference that's the key to every one of these problems, no matter how complex it looks. So let's see. For the horizontal component, we have 30 meters to the tree, our x component of speed, there is no acceleration, and we compute time. Vx is going to be the 20 meters a second times cos 50. Gives us about 13 meters a second horizontally. We know that distance equals speed times time, so time is distance over speed. And this gives us 2.3 seconds to the tree. We don't play any games with this number. There's no doubling it. There's no symmetry in this problem. This isn't a distance to the tree and back. It's one way. That's the time. We need 2.3 seconds for it to hit the tree. Okay, so now, for the vertical component, the dy is no longer the maximum height anymore. We are computing the dy 2.3 seconds into the flight. So 2.3 seconds into the flight, it hits the tree. The dy is down here. And my little orange vector has obnoxiously lengthened itself, and it's not pointing at the point of impact anymore. This is a problem in Google Slides. It's not me. Sometimes when you present, some things change their size for some reason. So this little orange height of impact should be ending at the little blue dot there. So we compute out our speed. We know the ball is falling. We know it has 2.3 seconds. We work out what the speed is in the vertical, and it's 15.3 meters a second. That makes sense. The horizontal speed is less than the vertical because this angle is higher than 45. So what altitude will the ball be at 2.3 seconds from launch? That will be the spot it hits the tree. Because in 2.3 seconds, it's going to be where the tree is. So we plug our numbers in, and we have initial speed times time plus a half at squared. A half of 9.8, it's 5. And I put the negative in there. I just took the plus 1/2 times minus 10 and bundled it all at once. Minus 5 times 2.3 seconds squared, and I get 8.7 meters. So we hit the tree 2.3 seconds into flight, and that has given the ball enough time to come back down to 8.7 meters. What if we wanted the maximum height? Well, then you just recompute by ditching the time and putting in VF equals 0. You're not going to be able to find the maximum height by going, ooh, if it reached the tree in 2.3 seconds, maybe it was at max height half of that. No, the tree is completely destroying any symmetry in this problem because it's chopped off the parabola here. So if you want the max height, you ignore the tree and you go for a vertical speed of 0. Desmos is a great program if you know how to use it. And here's an example I did in Desmos. All right, this is not the trajectory. This is a distance time graph, not a plot in space. So what I did is I put a vertical mark at 2.3 seconds, and then I took our information, d equals VIT plus half at squared, and I plotted the vertical position in time, which is the parabola, and I put this 2.3 second mark here, and sure enough, the vertical motion of the shell intersects the 2.3 second mark at exactly the height we predicted. You have to try this yourself a few times to really get the hang of it. Now we're going to change it up a bit. We're going to launch from a height. We launched from the ground and struck a height. Now we're going to launch from a height at 3 different angles. In all cases, everything is the same. You're going to have a vertical and a horizontal component, and the vertical component, since nothing is interfering with it, will determine the time of flight. Once you have the time of flight in the vertical, then that's your time of flight in the horizontal. Are you going to be able to play the symmetry game and double the time of flight in this one? Not at all. The peak height in all of these problems is not halfway through the trajectory. The height at the peak doesn't even really exist for the first one at less than 0. So you're not going to be able to compute the time and double it. You're going to have to do some more thinking on this one to solve for it. Let's talk about elevated fire. You're shooting a cannon from the heights and you're elevating it. 200 meters a second, 75 degrees up. Let's calculate everything. Step 1, our X and our Y components. This means 193 meters a second vertically and 52 meters a second horizontally. Let's look at the symmetry of this problem and see where we can use it and where we can't. So we now have our vertical and our horizontal setup. We know a couple of things along the way that are going to force us to break this problem down. When we launch at speed, we'll reach a 0 speed at the peak. When it comes back down, my little yellow circle here, this thing is going to have the same speed at the moment it went up, but it will be downwards now. So there is symmetry there. We can break it down into pieces, but let's see how we go about doing that. First of all, we take our vertical. We have 193 meters a second vertical and minus 9.8 meters per second squared down. We cannot use the d equals vt equation because there's acceleration here. Now, this is very similar to the multi-part problems on slide 31, but that problem was straight up, straight down. This one is being launched at an angle. We're again looking at a path in space. So if you go back to the multi-part problems on slide 31, it will look similar, but it's fundamentally different from this one. We can do this in 2 steps. The maximum height will occur when the speed is 0. We run it through the time-independent equation, we solve for d, and we get a maximum height of 1,862 meters. The time of flight, we can get away with d equals v average t. That is not the same as d equals vt. d equals vt assumes constant speed. d equals v average t can deal with acceleration. We work out the time and we get 19.3 seconds to the peak. That is not at all halfway through this problem because it's not going from the peak and stopping at the yellow circle. It's got to fall all the way back down. So we are safe to say 19.3 seconds up to the peak, 19.3 seconds down to the same altitude, but it's going to continue to fall. So that's what I mean by the lack of symmetry in such a problem. So when we fall from the peak height, we're not falling from 1,862 meters. Remember, he's on a 100-meter tall building, so we have to add that 100 meters from the building height. We have a new problem now. The second phase starts at the peak height of v equals 0. That was vf in the first half. Now it's vi, and he's not falling 1,962 meters. You got to say minus 1,962 because he's going down. And this time, the acceleration due to gravity is helping. So we run it through this formula. Fortunately, with a vi equal to 0, the equation reduces to d equals 1/2 at squared, and we can solve for time. 19.8 seconds. Hey, how come in the first one you done solve for distance first and then you gone ahead and solve for time? Where when you get to this bottom one, you kind of like solve for time, because you like already knew the distance it was going to travel. So you're like, I think I'll shut up now. You see why I solve for time first, because we already know distance this time. Once we got the peak height, we know how far it's going to fall. We didn't have to do a distance calculation. It was already done. What about the impact speed? Well, there's a couple ways of doing it. Falling from 19.8 meters a second, can't we just do falling for 19.8 meters a second? Wait, no, you said I'm falling for 19.8 seconds, and I gain speed at 10 meters a second every second. Let's see, 10 for 19.8. That's 198. Oh, look at there. Came out just like this long one here. Yeah, 198 meters a second. It's going to sting when you land. Now, oddly enough, isn't that odd? It seems to have landed slower than it took off. Why could that be? We launched it at 200 meters a second, and it landed slower than it took off. Because we're only dealing with the vertical speed. Remember? We're not dealing with the total speed. This is straight up and down. So it did not land at less speed than it took off. It took off at 193 and it came down at 198. That still seems like very little added, but we can look at that later why it didn't do them that much. But you're not comparing this speed to the one up top. You're comparing it to the component speed. Now, there's also that the time up was 19.3 seconds and the time down was 19.8. Geez, that's hardly any difference. Are you telling me the time up to this peak was only slightly shorter than the fall all the way down? It's that diagram again in your brain. The building's 100 meters tall in my diagram. The peak height, where V equals 0, is 1,862 meters tall. Right? On this scale, this peak of this curve should be 10 times higher than the screen you're looking at. There's almost no difference. That building height is peanuts compared to the height the shell actually reaches. So not surprisingly, the time up to 1,862 meters took nearly 20 seconds. And then you're falling only 100 meters more than that. So the diagram is completely messing with your brain when you look at these numbers. Could we have done this problem in a single step? Is it possible to do it in one pass and not break it down into two? Yes. Not always, but sometimes yes. What we have to do is carefully track our position now. We actually have to do this as a vector numerically, right? Positive is up, negative is down. So the projectile starts at an initial position, DO, D original, D naught, is 100 meters up, and it will land at a position 100 meters down. Again, strictly in the vertical. We're not doing horizontal here yet. We're just doing the vertical. So how could I pull it off in one pass? You have to set up your equation. You have to set up your equation very methodically. You write it out like this. D equals 100 meters plus speed times time plus 1/2 AT squared. The trick is now the distance position on landing is going to be negative 100 meters. So if you put it all together, and there's no teacher that would ask you to maintain units now, you put it all together, very carefully paying attention to the integer numbers, gather everything all on one side, and reduce. And you might go, how did I reduce all that? Well, I done divide by what I could divide by. Okay? When I gathered terms, I divided out by 5. And you might go, but you got a fraction here, a decimal. You can do that. Why on earth would I want large numbers there when I could get rid of the 5? I divide this by 5, and the 200 divided by 5, and the 193 divided by 5. It gives me much smaller numbers to stick inside the quadratic. and you could convince yourself using the quadratic that I'm correct. Unfortunately, it doesn't really help us doing it this way, because now we've got the time of flight to the bottom, but you're typically going to be asked what is the maximum height, the time at the maximum, time to the end. So the one step, it's a good idea to be able to do it, but frankly, in reality, you're going to have to break the problem down in most cases, depending on how the teachers phrase the question. Now, of course, we switch our attention back to the x-axis. What did we have before? We got a vertical axis, had a 193 meters a second speed, and a time of flight of 40 seconds when we were done computing it all 2 slides ago. So we're going to use that 40 seconds now on this one, and it becomes dead easy. We're just taking the time, moving it forward, popping it into a single equation, and we get 2,080 meters. So this thing took off up to almost 2,000 meters in height, and it managed during that journey to have enough horizontal speed to travel 2,080 meters sideways. What I did here is I put on in Desmos the actual trajectory. Okay, this is a scale diagram properly of distance in the vertical and distance in the horizontal over the entire 40 seconds. There is no time in here. Okay, this is strictly a plot, like you photographed it and kept the lens of your camera open so you saw this great big streak of its flight. Where is the building? There. Now do you see why the diagram on the previous page could really mess you up? And why the building height is essentially irrelevant in this problem. So the fact that no textbooks use scale diagrams, you can see why, but can you understand you can do it in your head and realize the diagram on the page is leading you seriously astray? That's the diagram I gave you, and that's what it really looks like. So try not to let the diagram trick your eyeballs into outvoting your brain. Let's try this one now. Knowing the sneaky diagram that could not necessarily be correct. We're going to just shoot the thing straight off the cliff. Guess what? No trig is needed. How come? The angle's 0. There isn't gonna be any vertical. Now, here's the weird part. After suffering through those last couple of really difficult slides, a lot of students go like, well, what do I do now? What do I do now? You go back to the day before you learned this stuff. Very often when we just retreat backwards a little bit, it suddenly confuses you. You're like, how do I use trig? How do I use trig? Well, you don't in this one. Isn't that lovely? Same setup. Okay? No calculation needed. It's shooting to the right. All the speed is in the horizontal. None of it is in the vertical. Now, how long can it travel horizontally? Simple. How long does it take to come down and crash? That's determined by the vertical. Broop, 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 broop. Okay? 14 seconds to fall. Do we need to double that? Do we need to do anything with it? Absolutely not. 14 seconds, boom. There's no up and down path on this one. Maximum speed of fall, same thing. You can do that in your head. Fall for 14 seconds. I'm gaining speed at 10 meters per second. 140 meters a second. There we go. That's not too bad. Now the range becomes trivial. So when you suddenly shoot horizontally, if you've been doing a bunch of angled fire, sometimes your brain just goes, I must put trig in here somehow. And you'll try, but don't let that happen. This was pretty straightforward without the trig. Depressed fire. Some cannons, they get so sad. They just like droop. It's like we need Canon Viagra or something to like think. Let's say you're at the top of a tall building. You're like, hey, aim the cannon down. In the old movies, the cannonball would fall out the end of the barrel, which can't happen because what do you think the ramrod was for? You saw that. So now we're going to shoot down at 35 degrees depressed fire, 35 degrees from the horizontal, okay? And we're going to do the same thing. So I didn't know. What do you think the setup should look like? Ooh, there we are again. Our friends V sine theta and V cos theta. Something you must put in by yourself is that the vertical speed is a negative 115 meters a second. The only way the sine function would give you the negative is if you put minus 35 like a math teacher would ask you to do for an angle below the x-axis. I think you can use your intelligence from the diagram to go, this has got to be a negative speed. Same setup. All right, we're all set to go here. We got our speeds we've already calculated. Now, think about it. With this speed of 115 meters a second in the vertical, the building's only 100 meters high. You shoot the cannon down, so the vertical speed is 115 meters a second. Seriously, it's going to be less than 1 second, and it's going to be at the ground. And it's already moving so bloody fast. Even gravity is going to go like, whoa, it got right by me. I didn't even have any chance at all to accelerate it. So right off the bat, you should be able to see that this problem is going to be over with in under a second. And that way, when you screw up the math calculation, your brain can come back online and say, that's not right. So here's what I mean. If you get it in your head, you have to use the quadratic on this one. Because you have a VI and VF. Sorry. Now, why would I say use an estimate on this one? Well, look at it. There ain't no way around this one without the quadratic. We need to know our time, and we need to know our final speed, and we're kind of stuck right now. So you might get thinking you have to use this one. Our landing is 100 meters below. We're traveling at 115 meters a second. That's minus half AT squared. Drop the units, set up your quadratic. I divide it out by 5. Do a little calculation and get 0.83 seconds. Now the time is used in both sides. I'm not trying to be dramatic here. It's doing the transitions really slowly. You know how easy it would be to screw this up and get some bizarre time value? But your brain goes, this has got to last less than a second. And doing the speed, gravity barely had time just to tack on a little bit extra. All right, hardly much. 0.83 seconds. Why would it get much faster? Gravity didn't have much time. And then, oh gosh, to the horizontal. It's always nice when these problems end, because then when you get to the horizontal, it's just a straight calculation. So the horizontal speed, even though it was quite large, didn't even have a second. So again, don't turn your brain off. The quadratic is error prone. Some of these problems I've had to use the quadratic 6-7 times in a row before I got the right number that my brain knew from the get-go. And if it wasn't for the fact that I could use this little intelligence here to estimate the time, I would be screwed with the wrong answers all the time. Now, if we really want to up our game, this is getting more towards straight grade 12. We're going to try to figure out how to clear an obstacle. Can you deliberately fire over something? And there are people whose job it is to get rid of obstacles and fire over things. You would be surprised how far these weapons can fire. A standard M777 field howitzer firing a 155 millimeter charge. That's 155 millimeters wide back here. It's not the length of the gun. They can shoot 24 kilometers. Now, they have to start aiming pretty high to get those long ranges, but 24 kilometers is a good distance, and we're going to look at these ones next. we're going to take the M777 howitzer and play with its actual numbers about clearing an obstacle. So let's see the kind of things we would need to write down to range this all out. So the time of Passover is not the holiday. It's the best I could come up with. The time it crosses over the obstacle. And that will not be the time that Vy equals 0. That's what I mean by this. These subscripts are not supposed to be things you have to memorize. They're just convenient. So the time of maximum height, I could have written time subscript max h time Vy equals 0 for vertical speed is equal to 0. Over here, time of flight. Don't get all obsessed going, oh my gosh, where's the time of flight? When did we study that? They're just labels. For the altitude of the obstacle, we could call it the Y max, right? Which doesn't mean it's the maximum height. It's the maximum height of that mountain. I could take the range to the obstacle, call it R naught, because it's the range to the obstacle. And the full range, according to the specs on the gun, is 24 kilometers. The gun can fire at 827 meters a second, and it can elevate from 0 to 72 degrees, roughly, in height. We will see the real performance is extremely poorly modeled by this equation. This kind of departure is why I feel significant digits are meaningless in theoretical calculations. There's a lot more we should be aware of than how many digits we write in our answer. And you will find that thinking is much easier in many ways than the detailed work. You got to know what you're talking about. So we're going to take the Y speed on this 45 degree launch. That's what I'm setting it for. Right now I'm going to set for 45 degrees. That is going to give us our maximum possible range, and we will prove that later. When we do the vertical axis, we lay out our numbers, the calculated vertical speed, and now we can work out the maximum height. It's very similar to what we've done. We use the VF squared because we have no time yet, and we get 17,111 meters up, or 17,460 if you use 9.8 for G. It's really not much of a difference. So I put my calculated value in there, and we move on. Doing A equals delta V over T, we rearrange to solve for time. We know that it will stop at its peak, and it had a starting speed. And rounding gravity down, I get about 59 seconds for the time of flight to the top of its trajectory. Ignoring the wind resistance, this means this howitzer could clear a 17,000 meter high mountain in its way. That's pretty impressive, but we're going to see it's also an illusion. We switch to our X values. Now, it's not a surprise that at 45 degrees, it literally splits the velocity equally between them. A 45-degree triangle is a square shape, so you get identical values on your X and Y speeds. We set up our horizontal axis, which is way simpler. There is no change in speed, so I made the speed nice and big to make sure I understand there's no change in speed. And just to be extra super cautious, I throw an A equals 0. You don't have to do that, but this habit of wanting acceleration in a non-accelerated direction or putting constant speed where there is an acceleration, if you've been making that mistake, you've got to make it impossible for yourself to make the mistake. And a nice clean setup on the page will go a long way to stopping that. We're going to borrow the time because the 59 seconds to peak, this is giving us our time of flight. But we need to double it in order to get the true time of flight. 59 seconds up, 59 seconds down. So in the X direction, this projectile has 118 seconds to fly horizontally before it runs out of height. And the dx is very simple. There's no quadratic, there's no nothing else. It's just constant speed times time. We get 69 kilometers. Holy moly. Are we like bad with their math or something? We've got a horizontal shooting range of this thing of nearly 70 kilometers. That is like wildly off the actual real value for this device. It's incomprehensibly bad. Enough to give type A students night sweats. But this is totally acceptable. Range calculations don't use wind resistance, and they're going to be way the heck off real world values. For handguns, you will get more than 20 times the value than you would actually see in real life. And for these large artillery pieces, it's typically, well, look at the numbers, about 3 to 4 times too much. This is why I don't care for significant digits. You compute 69,030 meters. And if someone else argued with me, the rounding error we did by changing gravity to 10 would give us a time of flight from 59.69 seconds to 58.5. That's what rounding gravity did. Literally just changing it just a little bit over 1 second difference. That would cause an error in this calculation. From 69,030 meters, it would change to 69,837. Ooh, that's about an 800 meter distance. So, like, well, yeah, your children are rounded here at the wrong spot, and you're off by 800 meters in your calculation. But the real value is 24,000. You're so freaking off because wind resistance wasn't included. Tracking these decimal places is a completely foolish thing to do, because you're actually then trying to trick yourself into believing you should be getting a value like, well, the theory was we should have got 24 and I got 24.001, so I was close. That kind of kid will have a brain aneurysm when they get told the real value is 24,000 and they got 69,000. But that's totally acceptable. What this is telling you is you're missing something. Something else is affecting this. How do you think discoveries are made? They're not made by getting an answer that matches the existing answer. They're getting an answer that goes, whoa, that's way off of reality, and you go hunting down the new effect and you discover something new. That's the only way it happens, is trying to decide if the error you got is just due to floppy fingers on a calculator or whether there is a new discovery screaming at you in the data that you've chosen to ignore because you become obsessed with significant digits. I'm not saying significant digits have no place, but to develop your core understanding, they're in the way. According to the numbers I put on this page, the significant digits on this answer would say you would write down my answer is 69,030 meters plus or minus 1 meter. That's what the significant digits would say. And you could get some like physics engineer out of artillery school going, well, I've calculated and I should be able to drop the shell on the Germans within 1 meter accuracy, and instead of hitting Germany, you take out Paris. Right? So you gotta understand that there are other effects in the real world that change these numbers drastically. So the simple fact is we don't have enough math at our disposal to actually calculate the behavior of the M777 howitzer in real life. Does that mean we're failures? No. I think if you asked most people, how far do you think the howitzer could shoot? They'd probably go, a mile, and you'd both be like still closer with your math. This is the first order approximation, we call it. You've done your first calculation without other effects. Let me modify the numbers so we can calculate a clearance. So behind the scenes, I have to toy with my numbers to make it work. So we'll rephrase the question. Can a howitzer clear an 8,000 meter tall mountain located 25 kilometers in front of the gun? and we will use our calculated values even though they are unrealistic. Why can't I use the theoretical values? Or can the howitzer clear an 8,000 meter mountain located 25 kilometers in front of it? And we'll use our calculated values even though they are unrealistic. Why would I do that? Because the math is well into 3 and 4 years into university to actually use the real values from the real world. We would need pages and pages and pages to get the actual range of 24 kilometers. So we have to use values that we generated using high school math. We can't switch to the real values when there's stuff we don't understand going on. So we'll use this on the airless Earth. So let's be clear about the question. When the projectile is 25 kilometers along that dotted path, how high will it be? How far up in the air will it be? And will that be enough to clear the mountain? So it is the position along the x-axis that is the key. No longer is it the time of flight, it's when we are 25 kilometers along, what time is it and how high is the shell there? It's that setup. That is everything in the problem. Even if the math takes you longer, if you don't get that clear idea in your head first, you are wasting your time and confusing yourself if you just start scribbling equations. We set up the same problem as before. We're going to get our Vx and Vy. This time, we're going to obsess about the x component. We want to know when it is going to be 25,000 meters along the path. There is no acceleration in that direction. It's a ridiculously easy formula. It is going to take it 43 seconds to reach that mountain. And in real life, it won't. It's going to take like 3 or 4 times that time. But it doesn't matter. This approach works. There are restrictions. It would work 100% perfectly on the moon with very little error. Sure, the moon's turning, there's other things, but if we did this on the moon, we would get extremely accurate results. So at 43 seconds, how high up is the shell? That switches us to the vertical, and we use the time from the range. Now, last time we doubled the time when we went to the horizontal from the vertical. Would we have any reason to want to change the time now? Not at all. 43 seconds to the mountain is the time. It's not a special time like time to the peak and then double the time to come back down. This is one-way trip to the mountain. 43 seconds. How high in the air is the shell? That means we're computing distance. We've got all our y values here, and we start our computation. The final speed is unknown, so we cannot use these two equations. The only equation that's going to work is this one. D equals VIT plus half AT squared. We know time, we know acceleration, we know speed. We get 15,910 meters up. It cleared the mountain easily, in theory. It's way above the mountain. And it's moving really fast, not that we were asked for that. It's still got a fair amount of speed. In reality, it would not even, in reality, this shot would land the shell at the base of the mountain. It wouldn't work. It's beyond the actual maximum range of the gun. Doesn't mean this math is incorrect at all. It just means this math neglected air resistance. So real artillery computations are quite involved. But this is how we got our start into beginning to understand how to range projectiles. And now we're sending them to other planets, and they arrive 15, 20 years after we launch them, and they arrive within a few hundred meters of where we intended them to be. We'll get a bit more advanced now, and we're going to start straying into pure theory that you'll want to be competent at by grade 12. So we're going to choose a target. And what if you intended to hit a target at a known range? How do you hit it if the gun can only change theta and not its muzzle speed of 827 meters a second? So I've set up a graph on Desmos. This is to scale. It's distance versus distance, not distance time. So we have our altitude going up and down the page and distance or range going sideways. So let's say we have a target at range 45,700 meters. We're planning to destroy Gaston's School of Mime. We want to figure out the theta to hit the target. How high do we have to aim the gun in order to hit him when we can't change the muzzle velocity? So let's take a look, and we'll see that this only solves itself as pure math. When we try to set it up, you'll find you don't have enough information. There's simply too many gaps in the information I gave you to figure it out. You weren't told the angle. So we can't compute Vy and Vx yet. We're kind of stuck until someone tells us the angle. But we want to solve it because we don't know what the angle is. So we start playing around and cross our fingers to see what happens. And we'll lead you along this path. We want dx to equal 45,700 meters. In past versions of this problem, we used Vx and t to compute d, more like dx equals Vx times t. Can we go backwards and figure out the theta by going reverse, solving for Vx, knowing what V was, and find the theta? Yes. We're going to reverse the problem. We're going to try to solve for the time using the expression like this. And instead of plugging in a value that we computed earlier, we don't know theta, so we cannot replace a Vx with a calculated value yet, but we can take the formula for Vx and shove it in this equation. And we can say, listen, when you tell me the angle you're going to shoot, I'll tell you the time, but I'm not ready just yet. So we haven't computed time, we have an expression for time. And that turns out to be even more valuable than the computation giving us a specific value. We would be able to put in any angle, any speed, any distance we want now on a spreadsheet and get the time value. This is really important when we get a relationship instead of one example. So now we can start thinking about where the shell is vertically. I've written y. Why have I done that? Because we're on the y-axis. We can write distance, distance y. We can use y. We can use any letter you want. Don't obsess about it. If you don't like seeing it written as y, put it as dy. If you don't like that, put the word vertical on the page and use d underneath, and just make sure you keep the vertical and the horizontal computations away from each other. Now, at the point of impact, the height will be 0. So this equation we're going to solve when the height is 0 with the time, and it should solve something for us. So let's move forward and see what we had. We had this in the vertical. We're going to put 0 for the height when it crashes back to Earth. We rearrange our terms. Fortunately, one of the times cancels. There's a time here, 2 of them there. Oh, thank you, the quadratic isn't going to show up now. But we know an expression for Vy. We know that Vy is related to the full velocity by the sine of the angle that we don't know. So the best we can do now is get to this part here. We can say V sine theta is equal to 1/2 AT. And we're stuck again with the formula that could solve for time if we knew the angle. Now the last one, notice it had T is equal to the d over V sine theta. Not surprisingly here, for on the vertical axis, gravity showed up. It's hanging around because it's going to be doing something on the vertical. It's not magic why the acceleration is still present. Now, we know what time was. From the last slide, we have a solution for that letter T. We could combine these, like the old commercials where the girl is eating peanut butter out of a jar and the guy is walking down eating a chocolate bar. And you know, girls often eat peanut butter out of a jar with their fingers in the street, and the two of them bang together and he shoves his chocolate bar into her peanut butter container. And that's how the Reese's peanut butter cup was invented. What if we took our chocolate bar and shoved it into our peanut butter here? Could we combine these two equations? Why, certainly. Since we know this is true, I can just take the time and replace it. I can go in and take that time and knock it out with this expression. And then we get, wait for it, drum roll please. Ah! It's not getting any simpler, is it? But time is gone. Everything in this equation is now known except for theta. We have everything now but one. There can be only one if you are going to solve for it. We have a chance of solving this now. It took a little bit. It's probably shortened your lifespan. You're probably unconscious on the floor or texting like mad. But we suddenly got rid of all the unknowns but one. So we have a chance of solving it.
Here's your reminder.
Ready? Starting with this formula on the previous page, we start rearranging it. I'm bringing all the terms with V to one side. I'm keeping them shaded so you know the reds are for the vertical and the blue was in the horizontal. I'm going to continue to clear up everything to one side. I group my two V's into a V squared and I bring the 2 to the other side. Now we're just left with A attached to D. So we'll deal with that. Now we've got an expression stating D is equal to this expression. I'm going to keep gathering terms here, and I've done something that you would be puzzled with. I took the V squared and the A and I shoved them to the end. And I kept the 2 and the sine theta and cos theta together. Why would I do that? Something that will be brand new to you unless you have math 1 year in advance of physics. This is called a trigonometric identity or a trig identity. It turns out again in the past, people with no social life whatsoever tried to figure out if there were other ways around the trig functions. And it turns out if you happen to see 2 sine theta cos theta in your math, you can replace it with sine 2 theta. We don't have the time to go into that, but I'm telling you it's the truth. You can verify it on your calculator. Go ahead and take 2 sine 45 cos 45, multiply them together, and then try sine 90. You'll get the same answer. So we can simplify the formula to this. And just a slight more rearrangements in a form that you're more comfy with. Dx is equal to sine 2 theta v squared over g. Holy moly, we've got an expression for the range of a projectile, and it has nothing to do with time. We built it out, which is pretty important back when these equations were being developed and measuring time was done with your heartbeat. You actually have an expression for the range of the artillery piece that does not depend on time. Do you need to know this proof? By first year university, they would expect you to be able to manipulate this with ease. But for here, no. We would give you this formula. I have no real intention of using this formula with you in a lot because there's no thinking involved. It's just plugging the numbers in. So I have no reason to give you problems involving it. I'd rather you do the components. But there are many rearrangements of formulas that are so handy they get written down. And I'm getting a little bit dramatic here, but this equation started our journey to the stars. I mean, you really need Newton's law, F equals g m1 m2 over r squared, because that's where the little g came from. But really, when people are trying to figure out, like, hey, throw a rock at him and kill him, that eventually we would be using that skill to send probes to other planets. So we have a new equation that's time independent, and it says basically that the range of a projectile is how fast did you throw it, at what angle did you throw it, and what planet are you on. That's not too shabby for a quick and easy calculation. So this equation will be added to your basket, but I have no real intention of using it unless there is a call for it. But I'm not just going to give you examples using the equation because there's no learning once you have an equation like this. The learning was in the proof. And that's going to take you a couple of semesters or years to really understand that. Let's go back to the graph that I drew. I showed you that the blue line hit Gaston. He's not on here now because he's dead. We were successful in hitting them with the blue one. If we zoom in on the graph, since this is a scale graph and it's distance versus distance, the angle should match. And if we zoom in really carefully, you can see that near the 0, and again, stupid Google Slides, this triangle is right on the red line when it's paused. You go to presentation and it goes, I'm just gonna scamper off this way for no reason. You can see that that is definitely 45 degrees there. But as the projectile goes up, the angle is changing. So you could actually graphically figure out the angle that got Gaston by doing, what do we got here? 1.5 run and like 1, 2, 3, 4 up. You could use trig and find that angle. But now we have a formula that would do it. We're now going to try to kill Gaston. And it looks like I have a graphical solution. I projected the range of the M777 howitzer, and it looks like we can nail him where he's standing with a range that you can clearly see on screen. You could measure that angle with a protractor because it is a distant graph and it's to scale. So this angle you're seeing on screen is quite measurable by a protractor. So can we use this formula to work backwards to the angle? And the answer is yes, but you're not going to like it. And this is why I de-emphasize this formula in junior physics, because it's stripping the meaning away to a degree and it's replacing it with mathematical drudgery like the quadratic formula. And when we move into pure math manipulation, the actual real world stuff begins to slide away. Now, I'm not going to test you on what I'm about to do. You should be able to do it by grade 12. You really want to be able to do it by first year university, but there is no stress in doing it now because it's not going to count, okay? So if you don't follow, you're fine. We're going to rearrange and solve for theta. So we regroup everything like this. Ugly looking spud now, isn't it? I don't know what it is. It's tolerable when it's written this way, but when it's turned around like that, it just, I don't know, it's just looking messy. We flip it around so it looks civilized. And now we're going to go ahead and put in our values. And we put in the values we've got. We make sure we square speed. And then we get the sine of 2 theta. We hit inverse. We get 40.9 degrees. Now remember, what we've just solved for is twice the launch angle. So we divide it by 2 and we get 20.45 degrees launch angle. We'll get Gaston. I've always warned you, never treat the graphs like they are to scale, because they are often not to scale at all. This one is definitely 100% to scale. Does this blue line look to you like it's 20.45 degrees? How are we to interpret this? That angle is nowhere near 20.45 degrees. Just a simple little screen, rise over run, do the inverse tan, we get 68 degrees on that blue angle. That is really far off. What's going on here? What's going on is pure math. There's a third firing solution here. I should say second. The red line is the maximum range of the cannon. There are two ways we can get the cannon to hit that target. At a low angle of 20.45 and at this high angle nearly 70 degrees up. And this is similar to square roots. You know the square root of 9 is 3 or minus 3. And sometimes you have to bring that into play in physics. So how on earth do we get the sine function to spit out that high shot, this one? How do we get that one out of the solution when your calculator is only going to give you the low angle? Then you got to go back to this in math. You got to go back to the fact that any angle is equal to 180 minus the angle in the sine function. So in other words, sine of 30 is the same as sine of 150. And that's where the second angle is. So let's find it. If 2 theta, our original angle, is 40.9, then there will be an identical solution at 180 minus that angle. So 180 minus 40.9, yeah, I wrote it in wrong. Then twice the angle, twice theta, is not only 40.9, 139.1 will work. So that is double the second angle. So the second angle that works is 139.1 divided by 2, which is 69.55 degrees. And that exactly matches what we measured off here. I set it to be 70 degrees when I did the problem. And when we reverse it out, even with rounding, we get 68 degrees by looking at the graph by eye and doing an inverse tan, and we get 69.55. Now, at what point did you cease doing physics and you just start doing math? So you can see why I limit this one, that I just feel that it's wades you into geometry to the point that you lose the physics. So I rather do these problems by doing the solutions in the X and Y plane rather than applying this formula and manipulating it and forgetting about the physics itself. But you will be expected to use the formula successfully next year and into first year university, and you need to get your trig skills up. What's it going to cost you if you can't do it in grade 12? Couple of percent, probably, depends on the teacher. So you've got a year for this to like digest with you, so don't panic. But this would be sort of like the high end of projectile math for high school.